on the interwebs. I was laughing because, you know, if I don't know if you guys follow the news or anything, but like all these, I mean, I guess I've only, and maybe other people say it too, but you hear all these people complaining about the voting, that we got to count all the votes and something. And I started thinking, do you realize that it is absolutely mathematically impossible that at any point in history, every vote was counted on election day? Does that even make sense? Like, think about that. Now everything's electronic and digital, but imagine like 100 years ago, do you think that they were counting every vote? But at the end of I'm not saying they weren't counted eventually, but you understand what I'm saying? Like, anyhow, I find this funny, but in it is what it is. But the official vote, this is hysterical. You know, we should watch it on YouTube. In Francis McClure Elementary today, coming in third place with only one vote, Kanye West. Coming in second place with 187, Joseph Biden. And in first, by only a 4-vote margin, Donald J. Trump at 191. Can you imagine? What a time to be alive. Now, of course, will that predict? That probably is what would happen in that part of the school district. Trump would win slightly. Because you figure these kids probably vote who they think their parents talk about, right? Well, yeah, well, that's actually pretty wise. I like that. Well, Kanye is an absolute, years ago I used to call him a space cadet because he is, but now he's officially a space cadet. But it is what it is. Did you vote? Do you guys vote? I don't even know. Did you vote today? You should have, even if you voted for me or for Kanye. Oh, is that it? I actually got, I was there this morning. I was surprised there was a line. There's never a line at my place, but there was a line this morning. I waited 40 minutes, but I voted. All right. Let's do some math. So I got a couple things that we need to point out that I think this is confusing. So we need to understand this. First and foremost, I've got a few emails from people. There is a final in this class. So I think what's confusing some students is I know that the way that we're doing the semester, it's not that the semester ends before Thanksgiving, right? Do we understand this? It's just that we no longer meet in person. And I think each class is going to be different on how they operate. I think we're supposed to still go, as far as I know, until the traditional time. So you'll have a final very much like your midterm where it's a take-home thing, open book, open notes, whatever. And then you just submit it. So hopefully everybody understands that. And so there's, from the way I understand the rules, and I will clarify, but there's no in-person class after Thanksgiving, one of my favorite holidays, the hypocrisy of Thanksgiving in the United States. So if you're unsure what that means, please reach out to me. And we will definitely give you more details of how everything's going down, and over the next few weeks. Okay, the next thing I want to do is I want to talk about this homework because a few of you reached out on emails about these problems, and so we should definitely talk about them. At least give you some hints. Let me pull up copy of it so I don't have to jump back and forth. By the way, while I'm doing this, do you guys have any questions about anything in particular? All three of you? What would happen, everybody? Oh, you want to see Halloween pictures? Yeah, we can do that for sure. Remind me before we leave. They're good. Our Halloween was a fun. It actually worked out well. Halloween. So, I think, when does the homework due? Is it due tonight? Is it tonight? All right. I mean, you can turn it in. If you don't finish it by then, you can turn it in tomorrow or whenever. Pretty lenient with that. I never finished your grades updated, huh? I think I need to do your quizzes now. You guys are like the worst of my lot. I never update you guys. It's very unfair to you. You're probably freaking out. You're like, where's my grade? What am I going to do in this? What do they say? No news is good news, right? Is it that way? People don't go to the doctors for that reason? They don't want Oh, and don't forget I posted that other little writing assignment, right? Didn't I put like a tell me about your life or how this class annoys you or like you like it? I don't know. For some reason this won't open and it's frustrating me. That's mean of me. I said it's due on election day. So anyhow, the first few problems on this homework were essentially what we've been doing in class. Here's a function, differentiate it twice, tell us when it's increasing and decreasing, tell us when it's concave up, tell us when it's concave down, and then graph it essentially. So does anybody have a specific problem on that they're curious about? Or do you just want me to say what I had planned to say? I mean, it's up to you. Guys can ask a specific question. I'd be happy. I know some of you email me. I don't remember which problems you said. I guess I can look that up. Let me look that up right now. Yeah. Okay, so let's see. Oh yeah, this is so here's an interesting one. Funny enough, a few of you asked about number 2. So let's do number 2. Funny enough, this one is actually, I don't want to say it's a trick problem, but it's meant to be short. It's like, if you understand what's happening, it's a real quick one. So let me explain what I mean. Now, I'm not going to do the exact thing. So let's call this homework number 8 hints. So let's look at a function that's sort of similar to problem 2, part 2. So let's say 10x plus 3. Let's analyze it. I'm not going to write down all the things it asks you to do. We understand that. So I'll use a shortcut. I'll say let's analyze it. So the first thing that you need to see, and this helps make this problem real quick, is the derivative. So the derivative of this using the chain rule is 1 over 2 times this times 10. Now, I can simplify this. This becomes 5 divided by the square root. Now, this looks kind of like ugly, but the key observation that you have to get here is that this thing is always, always, always positive. So remember, when you're trying to find critical numbers, the thing is to get the derivative, set it equal to 0, and solve. Well, this thing doesn't ever equal 0. You can try to solve it if you'd like, but it just doesn't equal 0. The other thing, another way to think about what this thing is saying is, if you look at it, the numerator is 5, so that's always a positive value, clearly. The denominator is a square root. And in calculus class, we are only interested in functions that take a real number and spit out a real number, which means the context of this course, the square root of a number is always positive. And if what's inside of the square root is negative, we say it's not in the domain. So another way to think about this problem is the domain of my function here is only when 10x plus 3 is greater than or equal to 0. Does that make sense? So let me say this real, let me make it very clear. So note the domain equals this set. It's the set, well, let me not write it like that. That's a little scary. So let's just write it in English. The domain is all x. Now, what does x have to be for this to make sense? Well, if you set the inside to be greater than or equal to 0, you get all x greater than or equal to negative 3/10. Does that make sense? Anything less than that, negative 3/10, will result in a minus or a negative number inside the square root. So we just ignore those guys, right? Now, if you look at the derivative, the derivative's domain is very similar but not the same. It's all x greater than negative 3/10. Now, the reason I exclude considering negative 3/10 now is because if I did plug that in, I'd have 3 divided by 0, which is undefined. So the derivative is actually undefined at 0. And if you look at the graph, that shouldn't surprise you. Think about it. It's not an asymptote per se, but what you have is that it's becoming vertical. We'll see that when we go to graphing. Do you guys have a question about this piece? So you can almost argue right now that you're done. There's not much more to do. I mean, you could sketch this graph right now very accurately. Now, it doesn't hurt, though, to just be on the safe side and compute the second derivative. So let's make this very clear, what we have already. So since f prime is greater than 0 for all x in the domain, so let's be very clear. So let's say all x greater than negative 3/10, f is increasing on its domain. What's its domain? Well, its domain is this interval. It's negative 3/10, comma, infinity. So at this point, you can sketch the graph. Now, if I just do that briefly, now what happens when I plug 0 into my function? So I'm just going to get 1 point of some reference here. If I plug 0 into my function, I get the square root of 3. Right? So I know what I'm saying is I know that this thing goes through. I know that the graph has to go through this point. It has to go through the point 0, comma, the square root of 3. And so if I just want to be real sort of without thinking too deeply about this is what the graph looks like. It's always increasing, so it has to look like that. Now, if you want to be a little more clear, you could do this. You could say, okay, well, let's also compute the second derivative, just so we have a full, you might want to say, okay, is it concave up at any point? So notice the derivative is never 0, which means it can't turn around. It just has to increase forever. Now, if you want to understand how steep it gets, well, then you'd have to plot more points, but you get the idea, I think. Now, what about concavity? I mean, we do know it could. How do we know it doesn't like turn up and change concavity? Well, that would mean the second derivative would have to be 0. So let's look at that. Note, let's write down. I'm going to write the first derivative, but I'm going to write it different now. I'm going to write it like this. And the reason I want to do that is because it's just going to be a little easier for me to differentiate now. I didn't have to do this. I could have used the quotient rule or whatever, but I'd like to just use my friend, the chain rule again. So this becomes negative 5/2. Recopy what's inside and then subtract 1. So you get negative 3/2. And then this is times 10. So if I clean this up, and I'm going to write it a little differently, this is negative 25 divided by 10x plus 3 quantity to the 3/2 power. Once again, this thing is not hard to analyze. This number downstairs has to always be negative. I shouldn't say downstairs. The numerator is always negative, and the denominator has to be positive. So what is the third root? What is the 3/2 root? Or excuse me, the 3/2 power? Well, think about that. What that means is, that means you take the square root of what's inside, and then you cube it. So we already know that 10x plus 3 has to be positive because our domain ensures that, correct? And so that means that the square root is positive. And then if you cube a positive number, it's also positive. So what this tells us is f is concave up on -3/10, or excuse me, concave down, pardon me. That would have been bad. Concave down on this interval. So we know that it never turns and has a switching concavity. Does anybody have a question about this? A comment? If you're confused, I know I'm using some reasoning here. I don't need to even plug numbers into this because I know from the context that it's always a negative number. Now, it's not going to be as clear to you as it is to me because you're just not familiar with thinking that way. But you should start to understand that. You should think about, oh, I get it now. I see what he's reasoning. He's reasoning. I'm using number sense. I'm using my number sense to determine whether a fraction can ever be 0, which this can't. And then can it ever be positive or negative? Well, this has to always be negative. I need some chemicals. You guys have any questions? Fun times, huh? Okay, so we did 3 and 4 in class on the homework. I mean, I know we actually did 4, and I think we did 3, at least pieces of it. We might not have done it in this form, but hopefully you can check your notes. And so the next two are challenging. Problem 5 usually causes an issue because you guys are usually good at the first derivative with fractions, and then you make a whole mess of the second derivative. That's just what happens. You're in calculus. You stink at algebra and stuff. I mean, I don't know. Does that sound mean to say that? I mean, I think I told you guys, I sucked at it too when I was in your shoes. I've told students this in the past, and maybe if I repeat myself to you, I'm sorry. But one thing I did that I'm glad I did is somewhere along the line, I had a teacher or a professor that told me to save everything. So I literally, in my house, in my storage, like under my, I have like the way my house is, I have like a storage place under my steps. I have all these boxes of all my notebooks from college and graduate school, all my homeworks, all these things. And man, I suck too. I would write the most ridiculous things down like you guys do. But it's good I say that though, because it reminds me that at one point I was an amateur, right? I stunk. And so what you need to do is you guys need to remind yourself that you're not going to get these things right the first time necessarily, or the second time necessarily. That's just part of the process. So you can't get discouraged. You just got to say that's what it is. Remind yourself that most human beings struggle mightily to learn calculus. That's what it is. Anyhow, let's look at something. Let's look at this problem. We'll actually do it for you. So now we'll take this problem. We'll repeat it with, what was it? 2x squared minus 3x over x minus 2. So here's how I would think about this. The first derivative by the quotient rule, you take the bottom times the derivative of the top, which becomes 4x minus 3, ugly, minus the top times the derivative of the bottom, which is just 1. And then this is all over the bottom squared. So look, this is a mess. And so what will happen if I were to put a problem like this on an exam, especially if it were like a traditional in-class exam, about half the class would actually compute the derivative correctly. But only about 1% of them fools would actually get the next part right, because it's just overwhelming. There's a lot happening. And usually when we're under pressure and whatever, we mess up our algebra. But before I do anything else, it's in my best interest to try to simplify this. And so what I'm going to do is I'm going to multiply it out. I get 4x squared minus 3x minus 8x plus 6. And then over here, this is a place where most students forget that you must distribute this minus sign. The damn distributive law comes back to bite us so many times. And so this becomes minus 2x squared plus 3x. And then it's all over the denominator squared. And so a couple of these terms These two actually add up to 0, so they're gone. And then there's the like terms here. 4 minus 2 is 2, so I'm left with 2x squared minus 8x plus 6 all over x minus 2 quantity squared. Now, what happens here is if you don't have to look. Your job now is to solve. If you want to find critical numbers, there's nothing that tells us. Like in the previous problem, we could reason that the derivative was always positive. Can't do that right here. So we need to do a little more work. So does anybody have any questions about this calculation before we go forward? By the way, it's a good thing for me to point out. Look. The reason I assign homework when I do and make it due when I do, it's not by default, or it's not just random, it's by design. The learning happens if you try this stuff before you watch us do it together. That's the learning part of it. If you just wait for me to do it, then you're not learning anything. I shouldn't say you're not learning anything, but you're not maximizing your learning. So learning happens when you struggle to get something and you finally get it, or you struggle to get something and you see how it's done through somebody else's eyes. That's where the learning comes from. So you shouldn't get discouraged that you couldn't get this, but you should, if you've given in a good effort a couple times of trying it, then it's more rewarding now. You might not see it that way, but that's kind of how I think about it. Okay, so on the next page, what is this? 2 minus 8 and 6. So we need to solve f prime of x equals 0, which is the same thing as 2x squared minus 8x plus 6 divided by x minus 2 squared equals 0. And what I'm going to do is I'm going to notice that the numerator are factors. So the first thing I'll do is I'll pull out a 2. And this is actually this. So what's left is x. I'll go slow. X squared minus 4x plus 3. And I believe that this numerator factors into x minus 3 times x minus 1, I believe. We're going to double check that in a second. So I did that in my head quickly, so let's double check. X times x is x squared. 3 and 1 is 4. And then negative 3 times negative 1 is positive 3. So this is a very loaded sort of, this is loaded right here. There's all kinds of things happening here. All sorts of crap happening. So what this tells us is the following. Here's what we get. We can learn a lot from this statement. So we have two critical numbers. They are x equals 1 and 3. And also, f prime of x is undefined at x equals 2. So we can also be clear. Maybe I'll just write it this way. Let me be a little more clear. Or not maybe clear, because that's not unclear, but a little more, give more information. F and f prime are undefined at x equals 2. So the function's not defined at 2, which we hopefully we solved from the very beginning because it was divided by x minus 2. But we also have an x minus 2 in the denominator. So we have to be very careful that we don't sort of mess that up. Now, the reason I'm pointing that out, and some textbooks actually will tell you that you call those critical numbers as well. or the derivative is undefined. I don't like to think of it that way. However, what you need to understand is what happens when something's undefined. Well, one of the possibilities is there's asymptotes. And what that means, though, is if there's an asymptote somewhere, it is possible that the function changes sign where it's undefined. So when we go to make our table, our sign chart, it's possible that we have to, let me rephrase that. We should, when we make our sign chart for the derivative, consider the possibility that it changes sign when you move from one side of 2 to the other side of 2. Now, of course, if you went and graphed it, you might even, you have these ideas anyhow. But I honestly think, and this is just my advice, you do whatever the heck you want because it's technology's free now. Well, I don't want to say it's free. Someone's paying for it. I would encourage that you don't graph things first. What I would encourage you to do is you do the math. And then, get the drum roll and see if your math matches the Desmos picture or the graphing calculator. That's just my opinion, because then it's much more rewarding if it does. But then, because if you look at the graph first, then you have this sort of bias in your head that you're trying to get things to work out a certain way. And that's just my opinion. You can look at graphs all you want. I know it helps, and it's a good resource. It's a good tool, but I think it's more fun when you do the math and then it matches, your picture matches the calculator. But what the hell do I know? I'm just a math nerd. Yes. Okay, does anybody have any questions up to this point? I keep hitting the wrong button. All right. What did I do? I hit the wrong. What am I doing? That's the problem. I have too many keyboards up here. I hit the wrong ones. All right. So we need to go make a sign chart now. Or we could go right ahead and take the second derivative. Let's do a sign chart first, because that second derivative is going to be beastly. Oh, by the way, it's worth pointing out, look, I'm not going to lie to you. If I were doing this, if I had to compute the second derivative of this function, I would use software to do it. However, when you're doing this, one of the skills you're supposed to learn is to show that you can do it. So even if you decide to, quote unquote, I don't want to say cheat, but if you use software to compute derivatives, if you don't show the work, you're not going to get full credit. Is that clear? So you got to show the work. All right, anyhow, let's make a sign chart for this beast, 1, 2, and 3. So, by the way, you could see these problems take some time, right? So here's our sign chart. It can change signs in 3 places. It can change sign at 1, 2, and 3, which means I need 4, count them, 4 test points. So let's do f prime of 0. That's an easy one to plug in. So by the way, let's remind ourselves what f prime of x is. And as I said, it's always best, and this is just my opinion, it's best to leave it factored when you're doing this because it's easier to evaluate or look at the sign. So this is 2 times x minus 3 times x minus 1 all over x minus 2 quantity squared. So if I plug 0 in here, the denominator is always even, the denominator is always positive. And so what ends up I have 2 times -3 times -1, which is positive 6. And so this tells me that I'm increasing. Then I'll plug something like, I don't know, how about I plug in 3/2? That's halfway between 1 and 2. Downstairs is positive. Upstairs is not, though. So, or is it, right? So what happens between 1 and 2? Well, between 1 and 2, x minus 3, this factor is going to be negative, right? But this factor is going to be positive. Do we understand that? And so this tells me that we are going to be less than 0. Now you can find the number yourself if you wanted, but I don't think that's I think it's good. In my opinion, reasoning the sign is a better skill. Now I'm going to do 5/2. And once again, I know that this is going to be decreasing. This is negative. So I'm decreasing. And then lastly, I'll pick something. How about f of 4? F of 4, this is not hard to get, but we know if you just reason again that it's positive, and then you know you're increasing. All right. Does anybody have a question, comment? Yeah.
Shouldn't they all be f prime of?
Yeah, that's a good point. I completely forgot that. Sorry about that. Prime, prime, prime. That's a typo on my part. Mea culpa. Does that mean I'm sorry or something? I don't know. What the hell is mea culpa? That's something. Oh my God. I'm on my like 400th text message today. They keep calling me Christy. I don't know who the hell Christy is, but according to one of them, either the Democrats or the Republicans call me Christy, and the other ones call me like Larry or something. I don't know where they figure these names out. Love it. That's the saving grace of all this. No more commercials. Although you guys, do you even watch television? You guys probably just watch Netflix and stuff, right? They don't even have ads for it. Like I was pissed. I had to look at these two jabronis on my screen all day, every day. Sean Parnell versus Connor Lamb. All day, I have to see these fools on TV complaining about each other. Neither one of them was on my ballot. Right? Waste my energy thinking about these fools. Actually, they could be nice guys. I don't know. All right. So this was beastly. It was. We can make a couple very important things from this, though, which you should say. So this means we have a local max at x equals 1. By the way, that point is 1, 1. If you plug it in, plug 1 into here, you get. And then we have a local min at x equals 3. So that would be the point 3. We'll plug 3 in. If you plug 3 into your function, don't plug it into the derivative, but if you plug it into the function, you end up getting 9. Plug 3 in, you get 2 times 9 minus 9. That's 18 over 9. And then 3 minus 2 is 1, so you get 9. So again, I'm getting, the x coordinates here are the numbers 1 and 3. And the y coordinates, I'm getting these by plugging the x coordinate into the function. And here's another thing you can actually get from this chart, which might not be obvious to you guys. We have a vertical asymptote. Asymptote, what a word, at x equals 2. Now, you might say, how do you know that? Well, look what my function's doing. It's decreasing on both sides of 2. Try to draw something that does that satisfies that. You're going to see that the only possibility is you have an asymptote. And the reason for that is if you actually took the limit from the left and right at that point, you would see that you have one. All right, now, we could technically sketch the graph now. We have enough information here to sketch it. But we should, for completeness, take the second derivative, suffer through it, right? And then get to concavity, if anything, because the problem asked us to do it. So you got to get tortured once in your life. It's not the end of the world. All right. So let's do that. I don't even remember what the damn first derivative was. It's factored there. I don't want it factored. So yeah, 2 minus 8, 6. So here's another thing. When I go back to this, so let's analyze the second derivative now. So we know that f prime, what was it? It was 2x squared minus 8x plus 6 all over x minus 2 quantity squared. So I don't want it in the factored version now, because in the factored version, if I go to differentiate, then the product rule is going to come into play. So it's actually in my best interest to leave it like this if I'm going to do this by hand. So let's suffer through this torture. So the second derivative by the quotient rule is the bottom times the derivative of the top minus the top. Oh boy, the bottom times the derivative of the bottom. Now this one's brutal. 2 times x minus 2, and then it's just times 1. So we'll put all those chain rule elements in there, even though multiplying by 1 doesn't do anything. And then when I square the bottom, I end up with a power 4. So this is an atrocity, right? I ain't happy about this. You ain't happy about this. It sucks. But there's a little subtlety we can do to make our algebra a little better. There's something we could factor out, and it won't be as bad now. So this is a great, you could tell this problem is straight out of a textbook. And the reason is because it works out nicely. Of course, you don't tell that. I can tell that. Well, maybe you can. Maybe like, how do we get these nice round numbers? So look, here's what I want you to pay attention to. Look at the factors upstairs. I have x minus 2 here. But I also have, there's an x minus 2 hiding in here, because if I factor out a 4, I have an x minus 2. And then I have an x minus 2 over here. So what I can do, and this is, I'll go very carefully. I have, if I pull a 4 out of the first guy, I have x minus 2 cubed minus. Now, what can I do over here? I'm going to pull a 4 out. I'm going to pull this 2. This 2 is already outside. But now I'm going to pull another 2 out of here like I did before. So, and we also know that this thing factors. So this thing is 4 times x minus 3 times x minus 1 times x minus 2. So that might not be so obvious to you, but I'm taking advantage of that. I've already factored that polynomial before. So I can use my previous knowledge to rewrite it like this. This is a hot mess, by the way. Now, I didn't necessarily have to do that. In fact, let me be clear, it might actually be better for me not to do that. I don't know. Because I might have to multiply those creatures back out again. So maybe, just maybe, it would be better if I would have left it with, pulled the 2 out. So the 4 here comes from the 2 in here, and then there's also 2 here. So now what I'm going to do is I'm going to pull an x minus 2 out of everything. So again, I can pull an x minus 2 out of here because there's 3 of them. And there's 1 here. So I'm going to yank those guys all the way out. I can also pull 4 out of everywhere. So if I go to the next page, and this is there's a lot happening here. This is 4 times the quantity x minus 2. Now what's left? I have two of these guys here. And then I have minus x minus 3 comma x minus 1. And then this is all over x minus 2 to the 4th power. And so there's a little more algebra that I can do because this creature and this guy, that little magic occurs. So look, it turns out that I shouldn't have factored that piece on the right-hand side because I'm going to have to multiply it out if I want to simplify this any further. So I don't have, you know, so I made a mistake. Well, I shouldn't say I made a mistake. I jumped the gun. I thought I was going to help myself, but it turns out what I need to do is multiply these out. So I get x squared minus 4x plus 4. And then this is minus x squared. So it's going to be inside, it's going to be plus 4x. And then it's going to be minus 3. So that one, you might notice that I did a couple things at once. But luckily, a lot of these bad things disappear. That's always exciting. You're left with 4 times 1. So this literally, so we're literally left with 4 times 1. So this is 4 over x minus 2 quantity cubed. Wow. So that one we might have to check because it seems like that almost seems too good to be true. Did anybody else get this, by the way? Or maybe did you? So I feel, well, at least 2 of us did, right? Did you happen to check it with like any software or anything? Or you don't do that? Some teachers probably would be mad at you if you did that. Let's see something. I think that's correct. What was our function? What was it? 3x squared, 2x squared, yeah. Minus 3x divided by x minus 2. I think that's correct. We'll check with the authorities. Yeah. What? Not any. Now, if we believe this to be correct, I think it is. Now, here's one where you might get a little, if you learned anything from the first problem we did, you might think that this guy, you'll be easily able to analyze this because here's the thing, the numerator is always positive. So here's what you can determine right away from this thing. F double prime of x is going to be less than 0 when x is less than 2, and f double prime of x is going to be greater than 0 when x is greater than 2. Now, I could make a sign chart if I wanted. I could. But it's unnecessary because there's not much happening here. The only thing you need to notice is the numerator is always positive and the denominator is going to be positive or negative depending on if x is less than 2 or not. Because if x is less than 2, you get a negative number downstairs. So you get that the value is negative. 4 divided by negative is negative. If x is greater than 2, then the denominator becomes positive, and 4 over positive is positive. Excuse me. So what this means then is we now have concave up. So we're concave up on 2 to infinity and concave down on negative infinity to 2. And so we can finally piece together what the graph looks like. So I could sketch the graph now. I'll make it nice and big because why not? So we know we have a maximum at 1, 1. So let's call this 1. We'll put this at right here. And then at 2, we know we have an asymptote. So we can't cross that. And then at 3, we know we have a local min, and that was at 3, 9. And so this is 1, 1. Now, if I just plug 0 into my function, for example, we know it goes through the point 0, 0. And because of my concavity issues, the only thing I can conclude, it's always going up till here, then it's going down, so it has to look like this. And then a similar scenario says that it has to look like this. So that's what the graph has to look like. I don't got any other options. Now, of course, it might be a slightly different shape if I look at, but that's the gist of it. And again, it should be very clear. These are nice and rounded curves. They're not V's. So this is a challenging problem, to say the least. But we should go to Desmos and check it out. And that's what we'll do. Well, I should share this with the peeps at home. So what was this? It was y equals 2x squared. And then it was divided by x minus 2. But it was a minus 3x here. So look, indeed. There it is. We weren't that wrong. Or we did a pretty good job. Let's see, 3, 9, 1, 1. I think that's something. That's always exciting when that happens. Wow. So if I were going to be honest with you guys, in my opinion, of all the ones in problem 2, this one requires the most work. It's probably the most tedious and pain in the you-know-what. The other ones actually the other one I got a lot of emails about was the last one, which we'll talk about in a second. Does anybody have any questions about this one? I mean, this one is mostly just a lot of terrible algebra, which every self-respecting person should know how to do. Okay, so very good. Let's look at the last one. This is an important function, and so I think it's worth analyzing it. The last one I asked you to do was the arctan. Now, once again, you need to know the derivative of this. So the derivative of this is not, you just need to know this formula. We showed you why it's true, but again, what's beautiful about this, look, can this thing ever be 0? HE double hockey sticks. It can never be 0. It's always positive. So F is increasing. That's good. Now, what's the second derivative? The second derivative, well, let's look at that. We use the quotient rule. You take the bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom, all over the bottom squared. So this guy is negative 2x over this. So again, this one, you can make a sign chart here. You can. It's not wrong. But if you think about basic numeracy, you don't have to. Because the numerator is the only thing that can change sign. The denominator is always positive. It's a square. The denominator is always positive, so we can conclude right away that f double prime of x is, be very careful, it is less than 0 when x is greater than 0, right? F double prime of x equals 0 when x equals 0. And then, of course, it's greater than 0 when x is negative. So be very careful with that, because if x is less than 0, it's minus 9, a number, minus 9. So if you have negative 2 times a negative number, you get a positive number. So here we know we're concave down. Here we are concave up. Now, you probably would not have thought to do it the way I just did it. So maybe you made a sign chart, and that's fine. But what I'd like you to do is understand that if a derivative has a very simple form, or the second derivative has a simple form, you don't need to waste time making a sign chart if you can reason in your brain. Now, I'm not saying that this is as obvious. The second derivative might not be as obvious to you guys, but I do want you to understand that you should, the first derivative sign, you should think about what I'm saying here. Like, the denominator can never be 0, and it can never be a negative number, which means this ratio always has to be positive. Now, the subtlety to this, which at this point, if you just tried to graph it, you wouldn't be able to graph it properly. Well, I'm not saying you should. That's a bad way of saying it. You would probably not graph it properly, because you would think since it's always increasing, it has to look a certain way. Now, think about this. If you're concave up but increasing, think about what that tells you. That tells you that you need to have or at least you think you would need to have a horizontal asymptote. So let's look at something for a second. Couple things to note, which you would probably not think about. Note the limit as x goes to infinity of the derivative, which is the limit as x goes to infinity of 1 over 1 plus x squared. This equals 0. Similarly, the limit as x goes to negative infinity of the derivative is 0. So what this tells us then is this suggests horizontal asymptotes. Now you're going to say, why does that suggest it? Well, think about the graph. If I tell you the derivative is going to 0, that means the graph has to be flat, right? What does derivative 0 mean? It means that the tangent line is horizontal. So this is kind of higher level thinking right here. This is not like 5 plus 7 is 12. Now we're asking you to really think. If the derivative is going to 0, that means the graph has to flatten out. And if you think about that, and you think about the function's domain, then you realize, oh crap, I get it. I see the final piece to the puzzle. And this is the piece that most of us don't think about when it comes to this function. What is the domain of f of x equals the arctan? Well, this is all x. But the range is not. What is the range of the inverse tangent? Well, graph the tangent. What's the tangent look like? The tangent looks like, let's go back to Desmos, because you probably forget this. What does the tangent look like? Y equals the tangent of x. Well, zoom in. We know the tangent has this period, so let's just look at one piece of it, the main piece. Let's look at this piece. It has vertical asymptotes, doesn't it? It's undefined at negative pi over 2, and it's undefined at pi over 2. So if that is the domain of the arctan, that means, if that's the domain of the tangent, then that has to be the range of the inverse function. Again, we're thinking at a little bit of a higher level. So what I'm saying is, do you guys remember when you first studied inverses in like an algebra class, they would say the graph of f and its inverse are reflected across y equals x? Okay, so let's do that. Let's graph, instead of the tangent, let's graph the arctan. There it is. It's reflected. So look at this guy. Now, if I draw two horizontal lines, pi over 2 and negative pi over 2, you will see that the green arctan graph is trapped in there. So what we're also telling you, what the calculus tells us, and this is not as obvious this is again a higher level of thinking, but what the calculus is telling us is the limit as x goes to infinity of the arctan of x equals pi over 2. And that's not just positive infinity, okay? And then the limit, if you go to negative infinity, we can argue it this way. We can just kill two birds with one stone. If I go to positive infinity, it takes, the limit is pi over 2. And if I go to negative infinity, it's negative pi over 2. So this is a fact that we can literally reason if we understand the calculus. Now, again, I'm not suggesting it's easy to understand the calculus here. It's a bigger step. But luckily, it's 2020, and you can graph the arctan and see that it's true. You guys have a question about this? Again, do not get, this is a difficult thing to work with here. Now, that being said, if you don't fully understand all the reasoning I did here, that is okay. What you should take from this, though, is that what the graph of the arctan looks like. In fact, this piece right here turns out to be quite useful when we do certain things in calculus, too. So. Okay, do you guys have any comments about this? I mean, it is kind of brutal. I feel for you, trust me. All right, any comments about this? All right, then I think we did problems 3 and 4 last week on the homework. So then that leaves, the only other question people asked about was the Usain Bolt one. But really, the Usain Bolt problem is no different than problem 4. It's just not stated with specific values, but it's the same thing. It's basically saying, okay, if I cover, think about, okay, well, I guess I don't want to say it's the same exact thing, but when it comes down to it, the reasoning comes from the mean value theorem. So here's what we know about number 5. And this is a good problem to think about, in my opinion. You cover, so let x of t equal the distance after t seconds. Okay? So I'm using seconds because that's what's stated in the problem. So for example, what is x of 0? X of 0 is 0. He didn't start running yet. This is one way to, I'm not saying this is the only way to solve the problem. This is just one way to think about it. All right, and what else do we know? We know that x of 9.8, we know after 9.8 seconds that he's gone 100 meters. Okay, so what does this tell us? Well, by the mean value theorem, there is some c, and c has to be some number less than 9.8 but greater than 0, where f prime of c equals, I'm not f, I'm using x, right? I'm not using f. So notice I didn't use f of x because I want to think of my variables time, so I'm going to use x of t. Maybe that's what's frightening. So we know that this has to be true. So another way of writing this is that 9.8 times x prime of c equals 100. Okay, so what does this really mean? Well, if my distance is x of t, and we're taking some liberties here. We're saying, okay, we understand he's running in a straight line. So what is distance? Well, distance, if my function x is my distance, then my derivative of x is the speed or the velocity. And so we want to know what's the maximum possible speed. Can we determine that from this thing? So again, I have the speed. So here's the thing to note. X prime of c is the speed at time t equals c. So the thing you're, okay, so what we're saying is that at one particular instance in time, he is running at, let's write, another way of writing this is 100. By the way, we should be very careful. We have 100 meters over 9.8 seconds. So using a calculator, one thing you reason is 100 divided by 9.8. So that is approximately 10.2 meters a second. Okay, so can we reason anything from this? So first off, let me be very clear what I'm trying to do here. All I'm saying is that at one point in time, he's going this speed. I didn't say that there's nothing that tells us right now, at least the way I've seen it, is that this is his fastest. All we're saying is that at one instance, he hits this speed. The question is, which is not what we haven't said yet, but if you go back to the question asks, I don't have it written down, but it says, what's the maximum possible speed? How do we reason that? So what we're trying to measure is we're trying to maximize the derivative, correct? So one way to think about this is here's one interpretation of this. If you look at the graph, is that his average speed is 10.2 meters per second. By the way, that's like over 20 miles an hour. It's pretty fast for a human being. So let's phrase it. So what you need to think about is how do you gain information about the maximum here? Anybody have any thoughts? Maybe we should leave this as like an extra credit problem. See if anybody can figure it out. This is a good one because if you Google it, you get a bunch of stuff that's not helpful. I mean, there's cool stuff if you Google this because people have analyzed this and there's all kinds of great exercises, not just in calculus, but in things like curve fitting, and it's pretty cool. Not just with him as a sprinter, but athletes in general. It's really cool how people study these things. So what we're saying now is, here's some hints, and we're almost out of time, but I think this is something, I'm not going to be mad if you never look at this ever again. I won't grade this. I'll probably grade it in terms of extra credit. And I can give away the answer at some point, but here's a good way to think about it. You know that at time, so suppose this is your time, and then this is your distance. You know that at 9.8, he's gone 100, right? So the question is, what does his, we doubt that his speed is linear, right? That probably, if you've ever ran as fast as you can, it's highly doubt that you've ran at the same exact speed the whole time. That seems sort of redunculous. It's possible that he starts off slower than speeds up. It's possible he starts up and then comes down like this. But what we do know is we know that at some point in here, his speed is at 10.2, and that we can think of that as an average. So maybe, for example, let's think perhaps this scenario where he sort of comes out of the gate maybe slower and then sort of speeds up and tries to hit his fastest at the end. I don't know. Or maybe he doesn't. I don't know. An interesting thing to think about too is how is this stuff analyzed in real life? Well, you could imagine that there is some sort of sensor, and every second you find his distance, or you collect data. And how do you turn that data into useful information? Anyhow, I'll let you think about this, and I'll give it away. If you're really interested, I'll send you, we could talk about it. But I think it's worthwhile you trying to ponder this. Problems like this, where it's not just some direct follow procedure, this is where you get some cool learning things. So anyhow, well, listen, we'll stop it here, and we will pick it up on Thursday. Hence I will have to show pictures then because we're out of time. I apologize. All right, guys, have a good one. Thank you. Stay out of trouble. Be safe. And I'll see you Thursday.